So, what exactly is this course about? Well, the title is Introduction to Symbolic Logic, and that's what it is. But what exactly is logic? You probably know that it comes from the Greek word for logos, logos, which usually just translates as word or sometimes thought, principle. It's the origin of our prefix ology, like in biology and zoology and psychology, which generally signifies the study of. But at its base, logos, logic, is captured quite nicely, I think, in this um, um, snippets that I've taken from the Oxford English Dictionary. So, three particular aspects of the definition that I want to draw our attention to. So first of all, it is a branch of philosophy. It's one of the so-called five branches of philosophy, together with sometimes what's called metaphysics, the study of being, epistemology, the study of knowledge, ethics, the study of human conduct, and aesthetics, the study of art and beauty. So it's the branch of philosophy that treats the forms of thinking in general, and more specific of inference and scientific method. So it's looking at those very building block concepts of thought itself and processes of thinking, usually in a kind of an idealized or an objective kind of way. So psychologists, for example, are quite interested in human thought and thinking as well. But often they're interested in terms of where our thinking goes kind of wrong or haywire, or the actual mechanisms, the brain processes that are involved in thought. Uh, Logic is interested in the structure of thought below that, or a more foundational level, thought itself, and especially inference, which we'll be spending a lot of time about, and and method. Second is this notion of logical argumentation. It's a mode of argumentation viewed as good or bad according to its conformity or want of conformity to logical principles. So there's an important sense in which definitions one and two are meant to capture a notion of the study of good reasoning. When reasoning goes well, how we can become better thinkers, better reasoner, better critical thinkers, how we can critique the arguments, the ideas of others. That's a focus on a logic that's kind of a practical focus. It's more associated with our second course in this kind of area, Philosophy 1175, which has now been dubbed critical thinking. Definitely in 1175, the emphasis is on talking about thinking as it occurs in kind of a natural environment through ordinary language and in our regular ordinary lives when we're trying to make decisions about what to do, when we're trying to understand the points of view of other kinds of people. We want to distinguish between good forms of thinking and poor forms of thinking. That's definitely the focus in philosophy 1175. It's not the focus in 1179, however. The focus in 1179, so we'll put that down here, is more this third sense, which is oops, a system of principles underlying the representation of logical operations and two valued variables by electrical and other physical signals as they relate to the interaction of signals. So those of you who are computer science students, you know how computer languages work. They are symbolic representations. You can manipulate them to do various kinds of things. Logic, in this sense, is the study of the ways in which those symbols can interact with each other to produce certain kinds of effects, a basic underlying structure. But it's not interested in the physical nature of the components used, so called hardware parts of computers. It's interested in the nature of the interaction of the symbols itself, so at a much more foundational or conceptual kind of level here. And it's this sense of logic that's contained in that notion of formal logic or symbolic logic. So the primary focus of this course is not to get you to be a better thinker, a better reasoner, make better kinds of choices. If that's the kind of thing that you want, then you're advised to drop this course and sign up for 1175. On the other hand, if your interest is in understanding the very basic structures of thought and reasoning and representation, particularly how they can be applied in practical kinds of ways, computer programming, mathematics, scientific reasoning, these sorts of things, then this is the course for you. It's our focus. So connecting that to modern computers, we're so dependent upon them in so many aspects of our life. I mean, the very fact that we can continue to have university courses in pandemic years is testament to the the ubiquity of sophisticated modern computers. But it's interesting that modern computers were not, I mean, they're kind of rudimentary mechanical computers, steam-driven computers that have been around for a few hundred years. But modern computers were not really possible until the full power of modern logical systems had been developed. And most of that got developed in about the first half of the 20th century. Still lots of advances and discoveries and applications and new things that are being learned in fundamental logic. But the bulk of modern logic was developed in the first half of the 20th century. And so, it's no accident that modern computers didn't arise until around the middle of the 20th century and have gained such a high degree of sophistication that we're seeing now. Nonetheless, modern logical systems, although they're developed in the first half of the 20th century, they grow out of, they fundamentally depend upon the most original logical system that was developed by Aristotle, the ancient Greek philosopher, student of Plato, teacher of Alexander the Great, way back in the 4th century BC, before the Common Era. And some of Aristotle's most fundamental, he was really the first person to systematize logic, to sit down and think about what are the basic concepts, how do they interact with each other, in particular, what is this notion of proof that's so important to logic. And those ideas are still the foundation of logical thinking today, and hence of all of the extensions that come out of it, including modern computer systems. So get a better sense of that. We're going to watch this little video. It's about 8 minutes long. I've got the link there. You can see it, but you're going to get recorded here so you can watch it over and over again. It involves just an introduction to Aristotle's main contributions to logic. Then I'm going to carry on a little bit past that to talk not so much about what logic is, but what exactly a logical system is. Keeping in mind that the fundamental aim of this course is to master the most foundational of all of the logical systems, first order logic. Okay, so I'm going to now stop sharing this screen, and then I'll share this little video.
Close your eyes. I want you to picture the knowledge that's in your head right now. Can you feel it? One way I can probe your knowledge is by asking you questions. That is, things you can know without leaving your chair, without interacting with the world in any way. None of your senses are allowed. Do you think this collection of knowledge can grow just by sitting there pondering to yourself? Now you can open your eyes. The process of going from question to a definite answer is at the root of logic. Logic explores arguments for truth. When we walk this pathway from question to answer, we call it reasoning. And logic is the study of sequences of reasoning. A big reason why Aristotle's ideas on logic matter today is because he steered the subject in what we'd now call the modern direction. He wanted to define perfect arguments for truth. So he looked for general patterns, that is, things that make something true no matter what subject you are thinking of. This is called abstract thought, but what exactly is abstraction? Close your eyes one more time. Imagine a tree you've never seen. Now you have some abstract concept of tree in your head, which was just activated. It's abstract because it's not a memory of a tree you've seen in the past. It's a more general concept or feeling of what you associate with treeness. With it, you can generate new trees in your mind you've never seen before. Now open your eyes. Your idea of tree is general enough to fit with any specific tree I show you. You can carry all trees in your head. That's abstraction.
Outdoor. Big window. Little house. Yes.
Children begin abstracting when they come to understand shapes and numbers as categories.
Can you make 2 towers?
Make 2. 1, 2. There you go.
And words or symbols act as the bridge between physical things and abstract concepts. For example, as a child you memorized the word tree, perhaps using a specific example, but tree became a label for your tree category. For Aristotle, it was important to separate these abstract categories from specific physical things in our world. He called this physical matter the primary substance, and the abstract categories in our mind as the secondary substance. You also have another word, human, which defines this abstract category which all people have existed and will exist belong to. What's important to see here is that the human category and the tree category don't contain any shared stuff. There are no human trees. But abstract categories can contain each other. For example, mortality contains both trees and humans. So these are the categories which Aristotle describes as secondary substances. And often when we are making statements about the world, we are actually just expressing connections between categories. And Aristotle shows this with a very simple example known as a proposition of the form all something are something, such as all humans are mortal. Remember, when we make this claim, we are saying that all things we could point to in the physical world will follow this pattern, while the opposite isn't necessarily true. So these statements are like building blocks for Aristotle. His whole system is built on a very simple rule about them. Valid statements must be true or false, but never both true and false at the same time, known as the law of non-contradiction. Next, he shows how we can then combine these statements to build new truths. And his idea is based on how we argue that something is true or not. If we try to make a logical argument, it means we are arranging a sequence of statements people already agree on as true and build to the statement in question. He thought of this as a perfect argument, since there is never a step where things break down, known as deduction. A common example, how can we prove that the statement, all Greeks are mortal, is true? To answer this deductively, Aristotle uses a conditional statement as the framework, which leads to the following form. If all, statement 1, and all, statement 2, then all, statement 3. And he puts the statement we want to prove as true at the bottom of this sequence. The process of deduction is to fill in statement 1 and 2 using knowledge which is already agreed on as true. So one thing we already know is all humans are mortal. Now we just need another statement which helps us connect Greekness to mortalness, such as all Greeks are human. If all Greeks are human and all humans are mortal, then all Greeks are mortal. The first two statements are known as the premise of our argument, and the third is the logical conclusion. If we can agree that the premises are true, then the conclusion must follow. This is known as a syllogism. But Aristotle only used specific examples to get people to his core idea. His big leap was to see that we only need to look at the structure of the words, not the content of the words. Remember, your way of representing the category Greek could be this combination of letters in English, or maybe you represent it as the color blue in some sort of color language. So now let's put together the same argument using this color system. Notice the colors bring out the pattern to his system more clearly. We connect blue-green concepts using a shared yellow concept, known as the middle term. So the final step Aristotle took was to remove the content of this argument from the form. That is, forget what the colors even represent. Think of them as variables. So any words or categories you choose to replace the colors blue, yellow, and green will still result in a valid argument leading to some true statement. Try it. Syllogisms, while simple, are important because they act as building blocks for even more complex arguments, allowing us to chain together statements which connect and quantify any abstract ideas we want. Logic allows us to reason about the world abstractly without any physical basis. We can just sit in our chairs and expend energy on abstractions. But what is the limit of logic? That is, are there some true statements which are out of reach of logic?
Hi, everyone. You might notice a little change of continuity. I had to edit this video a little bit. A lot of important things came out of that film. The first place to start is the idea that we have different ways of coming to know things. On the one hand, we can come to learn new things through experience or perception, just going out and looking at the world. But more importantly, for our purposes, we often come to learn new things on the basis of other things that we know. That is through a process just of pure reasoning or thinking. And Aristotle was the first to kind of characterize logic as the study of the sequencing of reasoning and develop some of the main core ideas and concepts and methods by which we can understand that process. The three main elements that come out of that film clearly that will come up for us again and again and again in this term are these. First of all, the logical processes of reasoning involves a considerable amount of abstraction. So we can represent ideas and beliefs and claims, and the idea is representation from a logical point of view is abstract in that it is completely independent of any particular subject matter. So logical representation isn't about anything in particular. And as a result, it can be used or applied to any subject matter whatsoever. And we're going to see that over and over again this term. Secondly, the process of sequencing of reasoning is a deductive process. And we'll be talking a good deal about what deduction is and how it differs from other forms of reasoning later on in other courses. But the idea of a deductive process is that new truths can be built out of old truths by a particularly rigorous and reliable method. Quite simply, when it succeeds, it's impossible to go from truth to falsehood if our system is purely deductive. And finally, Aristotle realized that what makes a system or a process of reasoning deductive, gives it that nature, is that reasoning depends solely upon form, not upon content whatsoever. And so he develops a system of logic that allows the representations it has to capture just the form. And as a result, it allows us to talk about anything whatsoever. And those are features that we'll see more and more as we go on. So that takes us to our first task. We want to understand a little bit about the nature of logic itself. And Aristotle gives us some very important insights to that, but he also develops a system of logic. So that leads us to a discussion about what our main task or goal in this course is going to be. And that is to develop and master the most fundamental of all of the formal systems of logic. The system that we're going to call first order logic, or FLO for short. But that raises the question about what exactly is a formal system, what makes a system formal in that kind of sense. So I want to get at this question of what a formal system is um, by way of two particularly famous, well-known examples. One will be somewhat familiar to at least most of you, and that is this ancient Greek philosopher's attempt, well, mathematician's attempt, to systematize geometry, and that's by Euclid way back in the 3rd century BCE. The second example is probably not as familiar to most of you, but it's just as famous in mathematical circles. And this is an attempt by a successful attempt by an Italian mathematician by the name of Giuseppe Peano to systematize arithmetic or basic number theory. And he does that in the 19th century. So I got a couple of videos that explain a little bit about these two examples. I'm going to show them to you, and then we'll stop and go over some of the highlights on them. So the first one two videos actually that will be linked that talk about Euclid's views on geometry and his attempt to create a systematic or formal system for geometry. Two videos. The first one is going to introduce us to three concepts from Euclid, and those are what he calls definitions, postulates, and axioms. Now, the definitions are going to represent the basic concepts of geometry from which ultimately all of the other concepts in geometry will be built out of. In terms of the postulates and the axioms, these really constitute the rules that Euclid proposes by which we can manipulate the concepts to produce other concepts and to gather that kind of new knowledge that we saw talked about in the Aristotle video. The second little video is going to be a representation or a description explanation of just one of those new bits of knowledge that we can get out of the basic definitions, postulates, and axioms. So it's going to work us through a proof of just one of his famous propositions, namely that we can that there are equilateral triangles and that they can be constructed in a particular way. Now, when you watch the Euclid video, it's I think helpful to understand or to approach geometry in the same kind of way that he did. So Euclid's coming at geometry at a time long before it was associated with numbers and measurements. So now, typically when we think about geometry, take an angle, for example, we conceptualize it in terms of how big it is or how we can measure it in terms of degrees. And so that uses number theory or basic numbers to understand, in this case, geometrical angles. Or we can measure the length of a triangle using a ruler. So that's a straight edge that's divided into units. And once we can do these kinds of measurements using numbers, we become familiar with some fairly basic geometrical notions. So, for example, the Pythagorean theorem, a squared plus b squared equals c squared, that tells us how to work out the length of any side of a right triangle as long as we know the lengths of any of the other two sides. But when Euclid was, first of all, approaching geometry, he didn't use any measurements in this kind of way. It was conceived to be quite different from arithmetic or numbers. Instead, all Euclid has to work with are really just two implements or two instruments, and the first is just a straight edge, and I don't mean a ruler in our sense. So like a ruler is a straight edge, but it's also divided into units, so it's got the numbers built onto it. So I'm thinking about just a straight edge, just a straight piece of metal or piece of wood. And the second thing he had to work with was a compass, which is just a way of creating circles. So when you're looking at these videos, it's all going to be constructed using just straight edge and compass geometry. Okay, so let's take a look at that now then.
Welcome to Euclid's Elements. Now, before we can learn anything, we must first know what exists and what the rules are in Euclid's world of geometry. So I will list some basic definitions to get us started, but I won't list everything because it's just too tedious. And what I really want to do is give you a quick general idea for what the elements is all about. So our first definition is points exist, and we label them with capital letters. Definition number 2, a line exists between 2 points. We call this line AB. Definition 3, a plane exists between 3 or more points. Definition number 4, when 2 lines touch or cross, angles are formed. When all the angles of the 2 lines are equal, the angles are called right angles and the lines are perpendicular lines. Definition number 5, with a center A and radius AB, we can create a circle. We call this circle AB. All radii of the same circle are equal. So that's all of our definitions for now. And we move on to some rules used within Euclid's Elements, and we call these postulates. Postulate number 1. Between any 2 points, a line can always be drawn. Postulate number 2. Given a straight line, you can always extend it by adding another point. Postulate number 3. You can always make a circle with any 2 points. Our last postulate, number 4, all right angles are always equal. Now, our last set of rules are called axioms, which are not only used within Euclid's Elements, but are rules used throughout all of mathematics. So our first axiom is, things which are equal to the same thing are also equal to one another. Now, an easy way to represent this is if A is equal to B and B is equal to C, then A is equal to C. Our second axiom says if equals be added to equals, the wholes are equal. So this means if A is equal to C and B is equal to D, then A plus B must equal C plus D. Axiom 3. If equals be subtracted from equals, the remainders are equal. So A is equal to C, B is equal to D, A minus B is equal to C minus D. Our last axiom is a special axiom which says that things which coincide with one another are equal to one another. We will leave the explanation for this axiom for later. So this is our list of definitions and rules which will help us create some very interesting facts in the next videos. You are now ready to learn Euclid's geometry. So now we begin with our very first proposition. And it states that with any straight line, you can always make a perfect equilateral triangle. So this is our given line, and remember, we can start with any straight line. So first we begin with postulate 3 and create circle AB. Again, we use the same postulate and this time create circle BA. Now, at the place where the circles intersect, we create point C. So next, we will connect points AC with postulate 1, and we will do the same with points BC. So now we have what looks like a triangle, but we do not know for a fact that all of its sides are equal. So next, we need to prove that this is actually true. So looking at circle AB, we can see that line AB is the radius. But we also see that line AC is also the same radius. So by definition 5, they are equal. Next, we look at circle BA, and we see that line AB is the radius. But we also see that line BC is the same radius. And again, by definition 5, they are equal. So we have line AC is equal to line AB, and line AB is equal to line BC. With these two facts, we can use axiom 1 to show that all three lines are equal. So now we know for a fact that all lines are the same length, and we have created a perfect equilateral triangle.
So, what was Euclid trying to do? Well, he was trying to produce a formal system that allows us to reason about all of geometry in our intuitive sense. Um, that, first of all, contains a very small number of basic concepts. Ideally, you want the smallest possible number of basic concepts, out of which your more complex concepts can be built. So, the video, he defined a point, he defined a line. That's the shortest distance between 2 points. He defined an angle as when 2 lines meet, they form an angle, and a plane is what happens when you've got 3 lines, the area between 3 lines. And from those 4 basic definitions, we can get triangles, quadrilaterals, cones, all kinds of different concepts built out of it. So that's one thing that a formal system tries to do. It tries to come up with the smallest number of basic concepts, or at least the very small ones, out of which more complex concepts can be built. Secondly, he establishes a set of rules for proving certain kinds of claims. For him, they were geometrical claims that start from those basic concepts, and those were the postulates and the axioms in his system. And you want those rules to be reliable, obviously. So we'll be talking a great deal about what actually would constitute the reliability of a set of formal rules or rules in a formal deductive system. And then the next thing he did, the bulk of his book, The Elements, and what subsequent geometers have done, is see what you can prove from the combination of those basic concepts and those rules. And he went on to prove a very long list of fundamental geometrical truths that we recognize today. And modern geometers are still finding new ones, quite surprising. We only looked at one example of the proof of the existence of an equilateral triangle and how to construct it using just the basic concepts and the rules. But there are a lot more besides. So it gives you a bit of a sense of what a formal system looks like, those 3 things. You want your basic concepts, you want establish some rules for manipulating those concepts, rules of proof, and then you want to see what you can get from them, what follows from them. The second example is a little bit less familiar to a lot of people, but probably just as important, if not more important, and this involves a great Italian mathematician, Giuseppe Peano. He tries to do for arithmetic, basic number theory, using natural numbers. He starts right at the beginning. Tries to do the same thing for arithmetic that Euclid had already done 2,000 years before for geometry. So we're going to look at this little video here. It's only going to describe the Peano axioms, and it's going to be limited to how they generate the natural numbers. Talk about exactly what the natural numbers are. It doesn't go on to show what we can establish, what further arithmetic truths that we can prove from there, but they can. And modern mathematicians use the Peano axioms to go on and prove the more fundamental truths of arithmetic. An interesting example. Bertrand Russell and Alfred White Northhead really developed their formal system that we're going to be learning first order logic. And they use Peano's axioms to prove the very astounding, surprising claim that 1 + 1 = 2, which turns out to be quite an important mathematical claim, even though it seems so obvious to us. But it's interesting that it took them 360 pages, starting from just Peano's axioms, to be able to prove that, which was regarded as one of the major achievements in logic and math and computing science in the 20th century. So much so that Russell goes on to win a Nobel Prize for Literature as a result of that. So I'll switch screens again and we'll take a look at that.
The natural numbers are pretty familiar. But if I asked you to tell me what natural numbers are and how they work, without using the notion of number in your answer, could you do it? In the late 19th century, mathematicians were on a quest to put all of mathematics on firm logical footing. Kelsey talked about this in a previous video, where she mentioned, among other things, that the number system can be constructed hierarchically, starting from the natural numbers and working your way up. But what about the natural numbers themselves? 0, 1, 2, 3, etc. Are they fundamental, or can they also be constructed from more basic ingredients? Before we can tackle that question, we need a firmer handle on what exactly it means to be a natural number. More specifically, we need a way to characterize the essential features of natural numbers without referencing, directly or indirectly, things that we already know about the natural numbers, because that would be circular. Now, it turns out that you can capture the essence of numberhood in a small set of axioms, analogous to Euclid's axioms in geometry, that will allow us to build a set n that behaves just like the natural numbers, without ever explicitly mentioning numbers or counting or arithmetic as we do so. These axioms were first published in 1889, more or less in their modern form, by Giuseppe Peano, building on and integrating earlier work by Peirce and Dedekind. I'm going to show you how this is done, but to appreciate what a massive achievement it is, I want you to try doing it yourself first. Just casually try describing numbers without mentioning numbers, or even inherently number-ish concepts like 1 or plus or next. You'll find it's pretty hard to do. First, some preliminaries. To make this somewhat self-contained, I need to assume your familiarity with some basic logical infrastructure that is not specific to numbers. First of all, you should be familiar with some ideas surrounding sets, namely that the members of a set are called elements, that two sets with an identical roster of elements are really the same set, and with the idea of a subset of a set, in particular, the fact that every set is a subset of itself. Second, we need a concept of equals. We'll be very bare bones about this, requiring only that whatever equality means, the relation be reflexive, symmetric, and transitive. And we'll also demand that the set n we're trying to build be closed under equality. In other words, if x is a thing in n and x equals y, then y is also a thing in n, because of course x and y are the same entity. Now that last part may seem self-evident, but when you're laying out mathematical logic, it's best not to leave any assumptions unstated, since that makes it harder to track which parts of an argument actually depend on which other parts. And finally, we'll also rely on the concept of a function or a map, i.e. a rule that associates an output with one or more inputs. Armed with these basic tools, let's introduce Peano's axioms incrementally, so that you can see exactly why each one needs to be there. Now, warning, some parts of the argument are subtle, and you may need to watch this more than once to keep up with what's going on. Let's begin. Axiom 1, Zelda is in n. This is basically a declaration that set n isn't empty. Zelda is in there. Who or what is Zelda? Don't worry about it. It'll turn out to be the 0 that you know and love, but I'm trying to use nomenclature here that's not too suggestive, so that you won't be tempted to bring in pre-existing concepts. Remember, the goal is to arrive at numbers without referencing numbers. Now, to populate the rest of n, we could just keep including the next element. But what is next? The whole notion of next is loaded with conceptual baggage that can be hard to disentangle from your pre-existing notions of counting and numbers. So that's what the remaining axioms will do. They will define next, using only more basic and non-numerical ideas. Let's see how that works, starting with Axiom 2. There exists a function s, whose inputs and outputs are elements of n. In other words, if x is in n, then s of x is also in n. Now, on its own, this doesn't buy us anything, because we haven't specified the mechanical rule underlying s. For instance, suppose that Zelda is in the set, and it turns out that s of Zelda equals Zelda. This would still satisfy axioms 1 and 2, but it looks nothing like the natural numbers. So let's fix that. Axiom 3. Zelda is never the output of s. More precisely, for any x in n, the statement s of x equals Zelda is always false. Now this is progress. Axiom 2 says that s of Zelda is in n, and Axiom 3 says that s of Zelda is different from Zelda itself. But notice that having s of Zelda turn out to be s of Zelda would still be consistent with the axioms so far, and that would bring our building process to a halt. So we need to prevent that possibility. Enter Axiom 4. If x and y are in n, and s of x equals s of y, then x equals y. In other words, different inputs to S will always give different outputs. Now finally, we're guaranteed an infinite chain. Watch. Zelda is in our set by axiom 1. S of Zelda is in our set by axiom 2, and it's different from Zelda by axiom 3. S of Zelda is in our set by axiom 2, and it's different from Zelda by axiom 3, and different from S of Zelda by axiom 4. Now we keep using axioms 2, 3, and 4 over and over. So S of Zelda will be in the set, and it's different from Zelda and from every element we've already mentioned, and so on and so on. This is starting to look like an infinite list of counting numbers. If we introduce some shorthand names for these elements borrowing Arabic numerals, like 0 for Zelda, and 1 for S of Zelda, and 2 for S of Zelda, and so on, it will look exactly like the counting numbers. Now what about the function S? Notice that we never specified its internal mechanics. We just enforced some constraints on its behavior that apparently capture the intuitive notion of next or successor, ergo the S. And we used as ingredients only the abstract concept of a function and the idea of equals. So we're done, right? Well, not so fast. There's a subtle loophole in axioms 1 through 4. Suppose that we throw two other characters into N. Let's call them Mario and Luigi. And suppose it turns out that S of Mario is Luigi and S of Luigi is Mario. Tacking on these plumbers with this weird S behavior doesn't violate any of the axioms so far, but it does leave us with a set that looks somehow bigger than the familiar natural numbers. So axioms 2 through 4 apparently do not quite capture the idea of next, because they would allow Mario and Luigi to be in the set but detached from everybody else, so to speak. To prevent this, we use Peano's fifth axiom, also known as the axiom of induction, which cleans up this mess by fiat in a very subtle way. Here's axiom 5. Suppose that T is any subset of N that satisfies two properties. First, that Zelda is in T, and second, that if X is in T, then S of X is also in T. Then, by declaration, T is the set N. In other words, axiom 5 declares N to be the minimal set that will satisfy axioms 1 through 4. Now, since the infinite chain we already have fits that bill, by axiom 5, that set is N. We are done. And adjoining Mario and Luigi along with their weird S loop would give you something different from N. So what does it mean to be a natural number? It means membership in a set that is endowed with the notion of successor, or next, and one of whose elements has the privileged status of not being anybody else's successor. Now, the miracle of Peano's axioms, in my opinion, is the revelation that next is not a fundamental concept, that it can be reduced to more basic logical ideas. And to me, the demonstration that this can even be done at all is one of the most beautiful arguments in all of mathematics. Now for some loose ends. First, what about arithmetic? It turns out that you can define both addition and multiplication solely in terms of the successor function S. Each of those operations, in fact, can be viewed as a function that takes two inputs from N and yields one output in N. And they can be defined recursively by the following rules. Now, I don't have time to do it here, but it is a fun challenge to play around with these rules in order to derive simple facts like 1 plus 2 equals 3, or that addition and multiplication are commutative and associative, or that they obey a distributive rule. Super fun. Second loose end. We arrived at a notion of successorship, and we built a set that contains entities related to one another by iterated succession. But we never specified what those entities actually were, what Zelda, or Zero, or any other members of N actually are. We just asserted that here's a thing, and here's some other things, and they're all in this set N. But we're leaving open the question, what are those things? Are they irreducible fundamental ingredients in the mathematical pyramid? Or can even these entities, the natural numbers, be built out of simpler entities in the same way that the integers get built from the naturals? We'll answer that next time, and I'll see you then.
We see a lot of similar features in this video that we saw with Euclid. The idea we want to start with a small set of very basic concepts from which more complex concepts can be built. In this case, the Peano was interested in trying to define the successor function, S, from which then addition and multiplication can be derived. And once you've got addition, you've got subtraction. Once you've got the negative numbers thrown in, and similarly, once you have multiplication, you also have division. So we can get uh, all of the major arithmetic functions as long as we can get that first function, the successor function. And then we establish a set of rules that allow us then to go on and prove various kinds of things. So a very similar kind of thing going on in Peano's attempt. Now, a couple limitations though. Peano's axioms are limited pretty much to pure number theory. And Euclid's are limited to pretty much the geometrical figures. So we don't quite get the level of fundamentalness that we want in our most foundational formal systems. We want to develop a formal system that, yes, lets us talk about numbers, but also at the same time, let us talk about geometry and to talk about anything whatsoever. So we want to get even more below those. But we're going to see our formal system is going to contain most of those same, or all of those same basic features. So we get a feel of what a formal system is. So here's what we want our fundamental system to do. I'll pull up that screen. We want it to do what Euclid and Peano are trying to do, but we want it to do it even more foundationally or more generally. So here, we want our formal system, first order logic, to be abstract enough to represent anything whatsoever, anything, at least to some degree. We want it to be foundational enough that it can establish the basic concepts and give content to them, define them in rigorous ways, particularly the concepts of truth and proof. We want it to be systematic enough that it establishes rigorous, reliable rules for proving things. We'll be returning to the notion of deduction later on for that. And finally, we want it to be embryonic enough that it can elaborate more so that more elaborate and sophisticated formal systems can ultimately be developed out of it. So our first order logic is very embryonic in that way. Ultimately, every other system of logic is going to be generated in some sense out of it. And they get to be quite sophisticated indeed, right up to various forms of quantum logics that are being developed right now, very sophisticated, complex sorts of things. In terms of a representation here, following very standard practice in most of these textbooks, we're going to get at first order logic, our most foundational system, from which other systems of logic are going to be built out of it. In particular, we're going to see that first order logic is an example of what's called classical or two-valued logic, but there are classical logics that are not captured by first order logic, but are still stuck out of it. And then we're going to see, other forms of logic. There are non-classical logics, there are deontic logics, there are tense logics, there are all kinds of other logics that get extended out of there. There are also deviant logics, non-classical logics, etc., etc. But our focus, of course, is we want this core here. But to make our lives even more simple, we're going to break down first order logic into two parts. The very smallest part, the core of it, is what we're going to call the sentential logic, or the logic of sentences. So we're going to be spending about the first half of the course looking at that. We're going to call it SL for short. We're going to see some real power to the sentential logic, but we're going to see some limitations as well. We're then going to extend that outward to capture what we're going to call the predicate logic, or sometimes called quantificational logic, the logic of predicates and quantification. It's going to completely subsume the sentential logic, but it's going to have some additional concepts, some more power. And put those two together, they're going to constitute first order logic. So that's our main goal. So roughly the first half of the course, 6 weeks, we're going to be looking at the sentential logic. Second half, we're going to be looking at the predicate logic, and that's going to be enough. And that'll give us a good grounding in formal systems at their most basic, foundational, embryonic, systematic level of all.